AWS has over 200 services. Now, most people think that learning AWS means that they need to be memorizing what each service does. EC2 does this, S3 does that, Lambda is serverless, pass the exam, get hired. That worked 5 years ago. It doesn't work anymore. And I know that because I have sat on the other side of the hiring table. I've watched person after person rattle off exactly what every AWS service does, and then they freeze the second that I ask them to actually go and design something. Because reciting what a service does and knowing when and why to use it are two completely different skills. I'm Sulaiman. I've been in tech for more than 11 years. Today, I run my own businesses across cloud and AI consulting, my software company, StudyTech.ai, and my academy, where I've helped more than 900 IT pros, engineers, and career switchers master cloud engineering and land six-figure roles, including at companies like AWS and Microsoft. So in this video, I'm going to teach you how to think through AWS like a real cloud engineer. We'll take 3 different business problems, figure out what's actually going wrong, choose the right AWS services, and build the architecture step by step. Firstly, we have a startup that's about to go viral. They have one server, no budget, and the traffic is about to jump from 1,000 users to over 100,000 users in a weekend. Secondly, an e-commerce company is losing $50,000 an hour when their site goes down. And finally, a Fortune 500 finance company with 40 people manually reading documents every single day. 3 completely different businesses in 3 completely different domains with 3 completely different architectures, but all of it using one simple framework. And I call it the decision stack. It shows you how to read a cloud brief, find the real bottleneck and the problem, choose the right AWS services, and explain the trade-offs like an actual cloud engineer. By the end, you won't just know what AWS services do, you'll know when to use them, why they fit, and what you're trading off. So let's start with the decision stack. Every cloud architecture breaks down into 6 layers. I call this the decision stack. And once you have it, you can walk into any problem that you've never ever seen and know exactly where to start. Layer 1 is traffic. This covers every journey that data takes, from a user opening the application and content appearing on a screen, to how your services talk to each other behind the scenes. How does the content get delivered so fast? How do you handle sudden spikes? How do different parts of your system communicate with each other? Layer 2 is compute. This is where the actual processing happens. When a user does something, clicks a button, submits a form, uploads a file, something needs to happen to handle that and respond. The compute layer is about choosing where that work gets done and making sure that it keeps working even when other individual parts will fail. Layer 3 is data. Now, every application stores information and it moves it around. The data layer is about choosing the right type of storage for the right type of information, making sure you never lose it, and deciding how information flows between different parts of the system, sometimes in real time, where one service waits for a response, sometimes through queues or events, where services work independently and pick things up when they are ready. Layer 4 is security. This is about controlling access at every single level. Who can use the application, which part of the system are allowed to talk to which other parts, and making sure nothing is exposed that it shouldn't be. You build this into every single layer from the start. Layer 5 is cost and budget. What does this cost to build and run right now, today? And if the requirements change over the next months and the years, how easy can you adapt things without rebuilding everything from scratch? Layer 6 is observability and monitoring. Once the system is live, how do you know it's healthy? How do you find out about your problems before your users do? And when something goes wrong, how do you know what to fix? The 6-layer decision stack: traffic, compute, data, security, cost, observability. Now, we are going to take this framework and apply it to the 3 real-world scenarios. Essentially, we are going to simulate what it's like being an AWS cloud engineer by applying our knowledge and understanding of AWS to solving real problems. The thing is, it is no longer enough to know what EC2 does or what S3 is. Instead, I'm going to take you step by step from the brief to the problem that we are solving, applying the decision stack, and then walking you through the architecture diagram as well. So stick with me here. Scenario 1, the viral startup. Here is the brief. A startup founder calls you. Their application is running on a single EC2 instance, everything on one machine. It handles 1,000 users completely fine. But they're about to launch a big marketing campaign and they're expecting traffic to jump to 100,000 users in a weekend. Their current setup won't be able to handle it. They need something that handles the spike and costs almost nothing when things are quiet because the budget is very tight. So when we get a brief like this, before we start drawing any sort of architecture or mapping any sort of AWS services, we have to take a step back and nail one key principle. And that's to know what exact problem that we are trying to solve. I know it sounds silly, but you'll be surprised how many people, even experienced engineers, jump to building a solution and architecture without really nailing down what the problem actually is. And when it comes to a job interview, if you skip and start drawing an architecture without clarifying what the problem is and understanding the requirements, you simply will not get hired. So here is the core problem. This startup's current architecture cannot scale, and they cannot afford to pay for capacity that they're not using. So that's the problem that we're going to be solving, because they're going to get an influx of users over the weekend. And we're going to apply our 6-layer decision stack to this. Layer 1, traffic. So right now, everything is running on a single EC2 instance. The website files, the application code, the database, all on one machine. So when a user opens the application, that one server is doing everything. Finding the right files, sending them to the user's browser, processing any actions that they take, and that's exactly why it cannot handle 100,000 users. It's trying to do too many jobs at once. The first thing we need to set up is Route 53. Right now, when someone types the startup's URL, their device needs to figure out where to go. That's called a DNS. It works like a phone book, turning a domain name into an actual address on the internet. And currently, their domain is pointing straight at that single EC2 instance. Every user, every request goes directly to that one machine. We are going to change where the domain is pointing to. Instead of sending everyone to the EC2, Route 53 will point them to CloudFront, which I'll explain in just a moment. This means that we control the front door. But right now, the immediate win is simply controlling where the domain results. We've taken control of how users reach the application. Next, we take the easy work of the service plate, the page layouts, the images, the buttons, the styling. Those are just files. They don't change based on who's looking at them. Right now, the EC2 instance is delivering those files to every single user who opens the application, and there's no reason for it to be doing that job. So we move those files into S3, simple storage service. Think of S3 as a massive filing cabinet in the cloud. You upload your files, they're available whenever someone needs them, and it costs almost nothing compared to running a server to do the same job. Now, S3 stores those files in the AWS region that you choose. That's the geographic area like North Virginia, London. Within that region, S3 automatically spreads copies of your files across multiple data centers for safety. So even if one facility or data center has a problem, your files are completely fine. But all of that is still in one part of the world. During a marketing campaign, users are going to be coming from anywhere, right? And if all of them are putting files from one specific location, someone on the other side of the world is going to have to wait. Slow loading times are incredibly frustrating, especially with all the brain rot going around. And if you're expecting to go viral, it means that you can lose a significant chunk of visitors who simply abandon the page before it even loads. And that means lost revenue. So always make sure that you tie things back to the business impact. So how we solve this is that we put CloudFront in front of S3. And this is what Route 53 is going to be pointing to. CloudFront distributes your content across what AWS calls edge locations. There are hundreds of these around the world, far more than AWS's main regions. They exist purely to get content closer to users. The first time someone in Tokyo visits the startup's website, CloudFront routes them to the nearest edge location in Japan. That edge location doesn't have the files yet, so it reaches back to your S3 bucket, grabs them, serves them to the user, and then keeps a cached copy locally in that region, right? So in Tokyo or Japan, meaning that the next person in Tokyo or Japan, or anywhere near that specific edge location, requests the same files, they're always going to be already there. So there's no round trip back to your S3 bucket in a completely different side of the world. It is instant. And then the same thing happens at every single edge location around the world as users in different places start to make their requests. This means that the startup's content is effectively everywhere, being served locally, and your original S3 bucket is barely being touched unless we've updated the application. And while setting up CloudFront, we want to attach WAF as well, the Web Application Firewall. A marketing campaign that goes viral doesn't just attract real users, it attracts bots, scrapers, and automated attacks trying to find weaknesses. WAF, the Web Application Firewall, filters those out at the edge before they even reach anything behind it. So just in the traffic layer, we've already made a massive difference. Route 53 is controlling the front door and pointing users to CloudFront instead of directly serving them from the server. Static content is off the EC2 and now being delivered globally through edge locations. WAF is filtering out malicious traffic before it gets anywhere near us. And then the server is no longer trying to do 4 different jobs at once. It can focus on the one thing it actually needs to do, which is processing the user actions like signups and form submissions. And that's what we solve in the next layer, the compute layer. So we've taken all of the static content off the server and it's now being delivered globally through CloudFront. But when a user actually does something on the application, say they click on sign up and submit their name and email, something needs to receive that information, process it, create their account, and send back a confirmation. That is the compute layer. And this is where we directly solve the scaling problem. Right now, they're running everything on EC2. Their servers run 24 hours a day, 7 days a week, and they're paying for it whether it's handling 10,000 user signups or sitting completely idle with no users at 3 a.m. And when 100,000 users show up during the marketing campaign, that one server will hit its limits and stop responding. So the current setup fails in both directions. They're paying for it when they don't need it, and it can't keep up when they do. The alternative here is Lambda. Instead of renting a computer that runs all the time, you write the code that should run when a specific thing happens, like an event, i.e. a user signing up. When that happens, Lambda runs your code, does the work, and stops. When nobody's using the application, Lambda isn't running, and you're paying absolutely nothing. And when 100,000 users show up at once, Lambda doesn't struggle or slow down. It just runs as many copies of your code as needed, all at the very same time, completely automatically. You don't set up any sort of scaling rules, you don't configure any thresholds, it just handles it for you. So for this startup, unpredictable traffic, tight budget, needs to handle a massive spike, we can go with Lambda. So we've now solved the scaling problem because Lambda scales automatically up to your account and service quotas. For a big planned launch like this, you should still load test, check concurrency limits, and request quota increases if needed. And we have solved the idle problem and wasting money if the server is running 24/7, because Lambda costs absolutely nothing when nobody's using your application. Both problems solved with one single decision. Now, Lambda handles the processing, but users can't automatically reach Lambda directly. Lambda doesn't have any sort of public address on the internet. It sits inside AWS, disconnected from the outside world. And that's actually a good thing, because you don't want your backend code directly exposed to anyone on the public internet. But it means that we need something in front of it and that users' devices can actually send requests to. That's the API gateway. API gateway has a public address on the internet. So when the user taps sign up on your website or your application, their phone knows where to send that request. API gateway receives it, and because it's connected to Lambda on the inside, it passes the request along and triggers the right function. Think of it like a reception desk that directs people to the correct rooms. And it's not just passing things along blindly, right? When a request comes in, API Gateway identifies what kind of request that it is. Is this a sign up, a login, a request for data? And then it routes it to the specific Lambda function that handles that action. So you might have one function for signups, another one for logins, another one for loading user data. API Gateway will make sure that each request reaches the right service. Now, there is something very important about Lambda that comes up frequently and often trips people up. When we say that Lambda only runs when something triggers it, that means that there can be periods where your function is sitting completely idle and nothing is happening. If nobody's using the application, there may not be any sort of execution environment running for that exact function. Then a user makes a request. AWS will need to create an execution environment, load your code that's running inside a Lambda, initialize the runtime, and prepare everything needed to run your function. AWS may need to create an execution environment, load your code, and initialize the runtime and prepare everything needed to run your function. This adds some initialization time, often a few hundred milliseconds because of the cold start. And that is what we call the cold start. At first, that sounds like a serious problem. Won't the user notice an additional delay? But look at where the cold start actually happens in the user journey. The user opens the application. The page, the buttons, the images, and JavaScript can all be served, you guess right, through CloudFront and S3. The application here is already visible and usable on their screen. The user then reads the page, they enter their email, their passwords, and then they click sign up. In this example, that is actually when Lambda is triggered. So when they click sign up, this is where the functionality happens and Lambda is invoked. Now, compared with the several seconds the user already spent interacting with the application, an additional few hundred milliseconds is unlikely to feel very significant. And AWS may then reuse the execution environment for later invocations. Right? So the first request is cold with the cold start, whereas the second request for the same thing is now warm. Like I said, for this type of application, cold starts are genuinely not a major concern, but the context really matters. Let's say you've got a real-time trading system, right? A multiplayer game or another latency-sensitive application. Even a small and unpredictable delay will not be acceptable because people are using the platform and they expect instant responses for these kind of platforms. Now, in those situations, you may choose a continuously running container service or another architecture designed to remain ready for requests. So the question is not simply whether Lambda has cold starts. The question is whether cold start latency actually matters for your specific application. Layer 3, data. We are now at a point where the user has signed up, Lambda has processed it, but where does all of that information actually go? Their name, their email, their password, their account details. All of that needs to be saved somewhere permanently. If we don't store it, everything disappears the moment that Lambda finishes running. Now, there are multiple types of databases and they work in completely different ways. For this startup, we would go with DynamoDB. DynamoDB is what's called a NoSQL database or NoSQL database. The simplest way to think about it, instead of storing data in rows and columns like a spreadsheet or a table, it stores it more like a dictionary. You look up a key like a user ID and you get back everything associated with that user, whatever that you stored against that specific key. It's extremely fast. It responds back in single-digit milliseconds. But the reason that we are choosing it for this startup specifically is that it scales the same way Lambda does, completely automatically. You don't need to predict how many users are going to be signing up this weekend. You don't need to decide in advance how much storage that you need. DynamoDB adjusts to whatever traffic is coming in. And that matters here because we genuinely have no real idea whether this campaign really brings in 100,000 users or 5,000 users or 50,000 users. Now, this capacity decision is actually worth pausing on because it demonstrates one of the most important principles in cloud computing, choosing an operating model that matches what you actually know about the workload. With DynamoDB, it gives us two capacity modes. We have on-demand and provisioned. With on-demand, we do not choose the number of reads and writes that a database must support in advance. We simply just pay for the request the application makes. If one user signs up, we pay for the right request generated by that exact sign up. So there is no capacity for us to manage and no fixed amount of throughput sitting there waiting to be used. Like I said, the second option is provisioned. With provisioned capacity, we specify how many reads and writes per second that we expect the database to handle. This can be a lot more cost efficient when traffic is steady and predictable, but it also means capacity planning becomes our responsibility. If we provision too little and our traffic suddenly spikes, requests may be throttled, right? And part of the application will simply just stop working. If we provision too much to protect against that spike, we also pay for capacity that most of the time is just sitting there being unused, meaning that we're just wasting money on capacity that we're not using. That is the problem for this startup. They're about to launch a new marketing campaign, but they have no reliable usage history. We genuinely do not know whether the campaign will produce 5,000 signups or 50,000. Starting with provision capacity would force us to kind of guess, right? We're just kind of guessing. If we guess too low, we create a reliability problem. If we guess too high, we create a cost problem. So what do? Well, we start with on-demand. We let the campaign run and collect real usage data. We observe how many requests the application receives. when the peaks happen, and how predictable traffic becomes. There is one exception here to keep in mind. If we are expecting an enormous planned launch that could produce traffic many times higher than anything that the table has handled before, we still check its warm throughput and prepare it for that expected peak. But for normal, unpredictable growth of this kind of startup, on demand is definitely the right starting point here. And then later on, once we have enough data and the workload becomes steady and predictable, we can then evaluate the provision capacity and use autoscaling and reserve capacity to potentially reduce the cost. The database does not need to change, right? We are simply changing the capacity model to match what we now know. That is the cloud engineering principle. Do not optimize around a guess. Start with the flexibility, collect real data, and then optimize for the workload that actually exists. Layer 4 is security. Security in AWS. Every service needs explicit permission to do anything, and the way you control this is through something called IAM, Identity and Access Management. The simplest way to think about it is like key cards in a building. Every person and every service gets a key card, and that key card only opens the specific doors that they need for their specific job. So our sign-up Lambda function gets a key card and lets it write to DynamoDB. That is it. It can't read files from S3. It can't access any other database. It can't touch anything else in the accounts. Then the S3 bucket gets its own rules. CloudFront can read from it and serve files from it, but nobody on the public internet can access it directly. DynamoDB has rules saying only our Lambda functions can read and write data and nothing else. Every single connection between services in this architecture has been explicitly allowed. If we don't set up the permission, it doesn't exist. But why does that matter? Because if something ever goes wrong, a bug in a Lambda function, a security vulnerability, anything, the damage stays contained. That function literally doesn't have permissions to affect anything else beyond its one single job. And nothing else in the system can be accessed by anything that isn't supposed to access it. The problem stays in one single room instead of spreading through the whole building. Layer 5, cost. So let's come back to the core problem. They can't afford to pay for capacity that they're not using. So what does this new architecture actually cost them? Now, Lambda gives you 1 million free requests a month. S3 has a free tier 2. DynamoDB on demand doesn't have free requests. You pay from the first write. But at low volume, those per request costs are pretty tiny. Right now, at low traffic, this startup is paying practically zero. When a campaign launches and the traffic spikes, they pay for exactly what they use. So every single Lambda invocation, every single DynamoDB write and read, every Cloudflare request. And when the campaign ends and the traffic drops back down, the costs drop with it. Compare that to the old setup, right? One EC2 running around the clock, costing the same amount every single hour, whether the application had 10,000 users or 0 users. This architecture will only cost money when it's actually being used by customers. Layer 6 is observability and monitoring. Now, the campaign is about to launch and they need to know what's happening. Is the application working? Are people signing up? Are there any errors? AWS has a service called CloudWatch, and that automatically collects data from every service that we've set up. How many times our Lambda function run, how many of those runs succeeded. We can set up a CloudWatch dashboard and we set up alarms, i.e. if Lambda errors suddenly spike, or if DynamoDB starts throttling requests, or if response times jump above a certain threshold. They get a notification immediately to their phone or to their email. Now let me walk you through the entire journey in full, from opening the application to signing up step by step. Step 1, the user taps a link or types in the startup URL. Their device does a DNS lookup, briefly free, resolves the domain and points them to CloudFront. This only happens once. After this, their device knows where to go. Step 2, the request arrives at CloudFront. WAF checks it first. Is it a real user or something malicious? If it's legitimate, CloudFront looks for the application files in the nearest edge location. If they are cached there, it serves them instantly. If not, it pulls them fresh from S3 and serves them to the user and then caches a copy for the next person. Their application loads on the screen. Step 3, the user fills in their email and password and taps sign up. Their device sends that request to API Gateway, which is the only part of our backend that has a public address. API Gateway identifies it as a sign up request and triggers the right Lambda function. Step 4, Lambda runs a sign-up code. It validates the information, creates the account, and saves the user's data to DynamoDB. Lambda's IAM keycard only allows it to write to DynamoDB. It can't touch S3, and it can't access anything else. DynamoDB's own permissions only allow connections from Lambda. Nothing else can read or write to it. Step 5, DynamoDB confirms that the data is saved. Lambda sends a confirmation response back through the API gateway to the user's device, accounts created, signed up. Across the bottom, CloudWatch has been collecting data from every service throughout this entire flow. How long each step took, whether it succeeded, how DynamoDB performed, all feeding into a single dashboard and alarms that we've set up. That's the full architecture for this scenario. It scales automatically, it costs almost nothing at low traffic, and if something needs to change later, say the startup grows and they need a little bit more complex databases for things like reporting across connected data, they can swap that one layer without rebuilding anything else. When you're learning cloud engineering and you're thinking about why you're choosing one service over another, what the trade-offs are, what happens if this component fails, you're already training yourself to think like an architect. And that does two clear things for you. It helps you get hired faster as an engineer because you're already demonstrating a level of thinking that most candidates are not having. And once you're in a role, you'll progress much quicker because you'll be already operating at a higher level than what's expected of you. So that architectural mindset approach is exactly what we focus on inside of my Cloud Engineering Academy. And it's why we are getting so many results right now. Rob went from technical support to hired as a cloud infrastructure engineer in just 7 weeks. And he even got a second offer with a base of $170,000. He came in, he acquired his skills with us, and became so good that he was able to build his own projects, which is the ultimate litmus test. Because at some point, you have to go out into the real world and solve real problems on your own. We're not here to handhold you forever. We are here to build you into an engineer who doesn't need us anymore. That's the goal. Mac went for IT help desk to systems engineer at AWS. Eddie went from a non-technical cybersecurity role to cloud security engineer with a $72K pay rise. Salim just got hired at American Express as a cloud security engineer, making multi-six figures. Silas switched careers at 42 and became a platform engineer. Dominic landed a cloud role at Siemens. Travel and Eric Tomislav all landed cloud engineering roles in just the last month. Are those results guaranteed for you? Well, obviously not. It totally depends on your experience and your starting point. But what we do give you is the right system and the right roadmap and the right support combined with a mentorship to get you into a role. So if you're actually serious about landing cloud role in 2026, then just book a call with my team, links in the description below. Scenario 2, the e-commerce resilience problem. Here is the brief. A mid-sized e-commerce company is running their website on a handful of EC2 instances behind a load balancer and a single RDS database. Everything is running in one availability zone. On Black Friday, their traffic tripled in 2 hours and their website crashed. They lost about $50,000 per hour of downtime. They want to handle traffic spikes in the future without wasting their money when their traffic is quiet. Now, this might seem very similar to the problem that we solved for the startup. They need to handle more traffic and they're worried about cost, but it's actually a very different situation and way more nuance, which I'll explain when we get to the decision stack. And I'm always going to show you something that separates the senior cloud engineers from the juniors, and that's the ability to not over-architect. Not everything in a brief is actually a problem that needs solving. Sometimes details are there as context. Sometimes, especially in interviews, details are thrown in there specifically to see if they will trip you up and send you down the wrong path. You have to read the brief, figure out what the actual core problem is, and then be deliberate about what you fix and what you leave. The core problem here is that their servers couldn't scale fast enough to handle the traffic spike, and that is it. The brief also mentions that they're running in a single availability zone. That probably didn't cause the Black Friday crash. The crash was mainly a scaling problem, but for a revenue-generating e-commerce platform, it's still something that we need to fix as part of the production design. Let's walk through the decision stack and see. Layer 1, traffic. Route 53 and CloudFront for static content, product images, page layout, styling, delivered globally through edge locations. We covered how all of that works in the first scenario, and the same setup applies here. But this company's traffic situation is very different. They're running multiple EC2 instances, multiple servers, all running the same application, and they already have a load balancer in front of them. But a load balancer on its own doesn't solve the full problem. A load balancer distributes traffic across the servers that already exist. It can check which servers are healthy, stop sending traffic to the unhealthy ones, and spread requests across the available fleet. But a load balancer does not magically create new servers when demand increases, and that's what likely happened on Black Friday for this company. Traffic tripled, but the load balancer kept distributing requests, but there simply weren't enough healthy servers behind it to handle the demand. Once every server was overloaded, the load balancer had nowhere to go to send the traffic. So the question isn't, do they have a load balancer? The real question is the load balancer properly configured across multiple availability zones? And is it connected to an auto-scaling group that can add new healthy servers when the traffic spikes? That's what we need to fix it. The application load balancer, or ALB for short, should be internet-facing, meaning that it receives incoming traffic from the outside world. Every request from every customer hits the ALB first. The ALB continuously checks which servers are running and are healthy. It directs each request to a healthy, available server. And if a server stops responding, the ALB detects it and stops sending traffic there. But the ALB is only half the story. The auto-scaling group is what adds more EC2 instances when the demand increases. Together, the ALB distributes traffic and the auto-scaling group changes the amount of capacity behind it. Now, all of this, the ALB, the servers, and the databases, needs to be organized and secured. And this is where we produce something called a VPC. A virtual private cloud. A VPC is your own isolated network inside AWS. You decide what is exposed to the internet, what stays private, and exactly what is allowed to communicate with what inside the network. Inside a VPC, you organize things using subnets. A subnet is a section of your network with its own routing rules. There are two main types here. A public subnet, which has a route to the internet, which means resources inside it can be made reachable from the outside world if their security groups allow it. And a private subnet, which has no direct inbound route from the internet. So resources inside it are hidden from external users. What makes subnet public or private is specifically the route table. Now, worth noting, services in a private subnet can still make outbound calls to the internet if you set something up called a NAT gateway, but nothing from the outside can actually initiate connection directly into them. It's a one-way door. So where does everything go? The ALB is internet facing, so it sits in a public subnet across at least two availability zones. It needs to receive requests from customers and keep routing traffic if one AZ has a problem. It's the only component directly exposed to the outside world. The application servers, i.e. the EC2 instances running the code, they go into private subnets. They can't be reached from the internet directly, and the only traffic they accept is forwarded from the ALB directly. And that's enforced by something called a security group. Think of this as a set of rules attached to a resource that says exactly who's allowed to talk to it. The database goes into the private subnet too. It has its own security group that allows connections from the application servers in the EC2 and nothing else. So you've got the layers. The internet can reach the ALB forwards the traffic to the application servers connect to the database. But you can't skip a layer. You can't go from the internet straight to the database. And each connection between the layers is controlled by security groups and the route table and explicitly define what's allowed. That layered network design combined with those security group rules is what keeps the whole system protected. Layer 2, compute. This is where the actual fix for the crash lives. The reason that they went down on Black Friday was very simple. Traffic tripled and they needed more servers to handle it, and they had no way to add them fast enough. Now, we used Lambda for the startup in scenario 1 because Lambda handles scaling invisibly. You don't think about servers at all, but Lambda has a hard limit on how long each function can run. 15 minutes maximum. So if your code needs to run longer than that to finish, Lambda will cut it off. This company's application is way more complex. It has specific software running on the servers, processes that needs longer than 15 minutes to complete, and dependencies that require a full server environment. Lambda wouldn't work here. So we stick with EC2 here. Actual virtual servers where they have full control over what's installed and how things are running. But we fix the thing that caused the crash. Right now, when traffic spikes, someone has to go manually into AWS, launch more servers, configure them, and register them with the load balancer. By the time all of that happens, the site is already down. Instead, we wrap the EC2 instances in something called an auto-scaling group. And here is how it works. You define scaling rules based on metrics, like how hard your servers are working, when the average CPU usage across all the servers goes above a certain threshold that you set, say 70%, then the auto-scaling group automatically launches new instances. Those new instances start up, they pass a health check to prove that they're working, and then they get registered with the application load balancer so they can start receiving traffic and serving customers. When the traffic drops and CPU falls below the threshold, let's say 30%, it removes the extra instances so you're not paying for them anymore. The infrastructure expands when the traffic increases and then contracts when the traffic decreases. And that's the core fix. If this had been in place for Black Friday, the auto-scaling group would have detected the rising CPU as traffic increased, started launching additional servers, and the ALB would have spread the incoming requests across all of them. That said, auto-scaling doesn't mean that you should stop paying attention. The team still monitors how the scaling is behaving, checks that the new instances are coming up healthy, and watches the application performance. The difference is that they're watching a system that's handling the situation, not scrambling to fix it last minute manually while the site is down. Now, remember the brief mentioned they're running everything in a single availability zone. An availability zone, AZ for short, is essentially a separate data center facility inside of an AWS region with its own power, its own networking, and its own infrastructure. The Black Friday crash was mainly a capacity problem, not an availability zone failure. They didn't lose a data center. They simply couldn't add enough servers fast enough. So the main fix still is auto-scaling, right? But for a revenue-generating e-commerce application platform, losing $50,000 per hour of downtime, keeping everything in one AZ is still not a good production design. So we don't overcorrect and jump straight into multi-region or anything like that. That will add way more complexity and cost than they need right now, but we absolutely spread the application across at least 2 availability zones. The application load balancer will sit in a public subnet across 2 AZs. The EC2 instances in the auto-scaling group will sit in the private subnets across the same availability zones, so if traffic increases, the auto-scaling group can launch more servers across both of those locations. And if one AZ has a problem, then the load balancer can keep routing traffic to the healthy instances in the other availability zone. Real quick, there is another compute architecture worth understanding here. Right now, this company is running what we call a monolith. We have user logins, we got the product catalog, shopping carts, and checkout, all part of one large application, right? It's just one application. These are all developed together and deployed together. And when the application needs more capacity, we have to scale the entire application. Now, a microservice-based architecture splits the responsibility of those features. So we have login, products, cart, all right, and checkout, which we covered. Login, products, and carts. Now, essentially what we're saying here is instead of having one large application handling everything, we are simply separating out the application and the features into smaller services. So we've got one service for user login, we got another service for product catalog, and we got another service for the cart. Each service can then be developed, deployed, and scaled completely independently. For example, if thousands of customers are browsing products and only a small percentage of people are adding things to their cart, we could basically just scale the cart service without actually touching any other part of the application. If the users are now suddenly all looking at our product catalog, we can then just scale the product catalog service to meet that demand and not touch any other part of our application. Microservices and containers are not exactly the same thing, but containers are one of the most common ways to run microservices. A container packages the service's code, the runtime, the libraries, and the dependencies together. That gives us a more consistent unit that can be moved throughout development lifecycle, right? From dev to test to prod, and it makes everything easier to push through our environments without having to rebuild that environment every single time. Now on AWS, one way to run these containers is using Amazon ECS with Fargate. ECS is responsible for orchestrating the application. We define each service, the container it should run on, how much CPU and memory that it needs, and how many copies should be available. Fargate provides the compute underneath those containers. It means we do not need to launch, configure, or manage the EC2 instances that form that container cluster. The ALB, the application load balancer, can then inspect each incoming request and route it to the correct ECS service. The application load balancer can inspect the incoming requests and then route it to the correct ECS service. A request to login can go to the login service. A request to product can go to the product catalog service. A request to checkout in the cart can also go to the cart service. Each service can run multiple container tasks across different availability zones. ECS keeps the required number of tasks running, replaces any sort of unhealthy ones, and can automatically increase or decrease the number of tasks as the demand changes. This is still very different from Lambda. With Lambda, we provide a function and AWS runs it whenever an event happens. With ECS and Fargate, we are designing long-running application services. We still choose a CPU and memory and networking and task count, deployment configuration, and even The scaling rules. Fargate removes the server management for us, but we still manage how the actual application operates. For this company, however, ECS with Fargate is not the direct answer to the Black Friday failure. Their application is currently a traditional monolith running on EC2. Migrating it into separate containerized services would be a much larger application transformation. The direct fix is still using EC2 with an auto-scaling group behind an application load balancer. But if the company later decides to break the monolith into independently deployable services, ECS with Fargate will be a way natural AWS architecture to then evaluate. Layer 3, the data. When the site crashed on Black Friday, the database stopped responding too. But that was almost likely a consequence of the compute layer failing, not the root cause. So here is what typically happens in this kind of chain reaction. When servers get overwhelmed, they can't scale. Each one starts making more and more requests to the database. Connections pile up, the database has a maximum number of simultaneous connections that it can handle, and when you blow past that, it stops responding. The database was under immense pressure because the servers in front of it were drowning, and drowning servers make terrible database clients. Does that mean the database has definitely no issues on its own? No, it could have potentially poorly written queries, missing indexes, or be undersized for this kind of workload. Those are things that you have to investigate once the system is stable. But the first priority of fixing is a compute layer because we're working our way down the traffic. Because until the servers can handle the traffic properly, you can't tell whether the database has its own problems or whether it was just being flooded with requests. With auto scaling in place, the compute pressure drops significantly. Traffic gets spread across enough servers, but each one is handling a manageable amount of work and making a normal number of database connections. That alone removes the most obvious source of database strain. If the database still shows issues after that, then you investigate it further. Query performance, connection pooling, instance sizing, but you fix the fire before you redecorate the kitchen. So we are not re-architecting the database to fix a crash, but while we are here, there is an improvement worth making that will make the system better going forward. Right now, the single RDS database is handling everything. RDS is a relational database. It stores data in tables like a spreadsheet with rows and columns. The power of a relational database is that you can ask complex questions across connected data. Show me all orders from this customer, which products in a category are running low on stock, what was the total revenue last month broken down by region, that kind of cross-referencing. Connecting the information across different tables is exactly what relational databases are designed to do. But not everything hitting the database is actually needing that power. Inventory lookups, for example, i.e. every time a customer opens a product page, the system checks the stock level. Every time someone adds something to their cart, it checks again. Every time a purchase completes, the stock number updates. These are incredibly simple, incredibly frequent operations. Look up for product ID, get a number back, no cross-referencing, no joining tables together, no complex queries, just a straight lookup. And right now, those fast, simple lookups are competing for resources with the other complex order reports and customer queries. So they're all hitting the same database, using the same connections, waiting in the same queue. By adding DynamoDB specifically for inventory, we separate those types of work. DynamoDB will handle the fast, constant inventory lookups, product IDs in, stock levels out, so it focuses on what relational database are built for, which is the complex connected data. Neither one is being slowed down by work that belongs somewhere else. DynamoDB is a right choice here specifically because the inventory and access pattern is simple. Look up a key and you get the value. If inventory needed complex relational queries like cross-referencing stock levels with supply contracts and purchase orders across multiple tables, DynamoDB wouldn't be the right fit for that. You'd keep it in RDS. The tool matches the access pattern, not the other way around. Level 4, security. So we've already built a lot of security into the network design. The ALB is the only thing that's internet facing, sitting in public subnets across 2 availability zones. The application servers are in private subnets, no direct route from the internet. The database is in its own private subnet behind the application servers. That structure gives us a strong foundation, but the network layer doesn't alone enforce security. We need explicit rules controlling what can talk to what. That's where security groups come in. A security group is a set of rules that you attach to a specific resource that defines what traffic is allowed in or out to the resource. Think of it as a bouncer at each door of each individual service. So the security group on our application servers will say that I only accept traffic that came from the ALB. Anything else trying to reach those servers get rejected. The security group on the database will say I'd only accept connections from the application servers in EC2. Not the ALB, not the internet. not anything else in the account, just the application servers. So if someone compromised the ALB, the database security group will still block them because the connection isn't coming from a recognized application server. The security groups are the main layer of access control around our resources. They're there doing the heavy lifting. On top of that, we've got the network ACLs, the network access control list. They add a broader filter at the subnet level. They're more of a safety net. Security groups are the bouncers at each individual door. The network ACLs are like a checkpoint at the entrance to each floor. They catch anything unusual at a wider level before it even reaches a specific resource. So two layers are working together. IAM controls what every service in each of the account is allowed to do once it's connected. The application servers have an IAM role that lets them read inventory from DynamoDB. So every single permission has to be scoped to exactly what the service needs for a specific job. Nothing more and nothing less. This is the same least privilege principle that we apply in the first scenario. The key card only opens the doors that you need. Level 5, cost and budget. So let's tackle the other half of that problem. They're not just crashing on busier days, they are overspending for the rest of the year. They've been running oversized servers year round because they're afraid of the next spike, paying for peak capacity every single day just to survive one single weekend. And it still wasn't enough, right? Autoscaling already fixes this. The baseline, i.e. the servers they genuinely need for a normal day, stays running. But we right-size that baseline to what they actually need on a regular Tuesday, not what they think they might need on Black Friday. Autoscaling adds capacity when it's needed and it removes it when it's not. Now, those baseline servers that run every single day, if they commit to using them for 1 or 3 years through something called a savings plan, AWS gives them a significant discount on that computing cost. The exact savings will depend on the commitment length, the payment option, and the instance types, but it can be substantial. The point is, these are servers that they're paying for anyway. A savings plan just makes them cheaper. The extra servers that add autoscaling adds during a busy period stay on regular on-demand pricing. So you only pay for them while they exist and then they get removed when the traffic drops. Committed pricing for the steady baseline. On-demand for the burst, so they're never overpaying during quiet months and never call without capacity during busy ones. If requirements change down the line, say they want a caching layer to make product pages load even faster, something like Elasticache can be added here. It would require some code changes to integrate, but it doesn't require tearing down the rest of the architecture. The layers are still independent enough that you can improve the architecture without starting over. Level 6, observability and monitoring. On Black Friday, this company found that their site was down from custom complaints on social media. That tells you everything about their monitoring. They effectively had none. That can never happen again. CloudWatch collects the data from the AWS services that we've set up, how hard the servers are working, how fast they're responding to requests, and how many errors are occurring, how many database connections are in use, and whether autoscaling is adding or removing instances. All of this feeds into dashboards, screens where you can see the health of the entire system at a glance. But we don't just track technical metrics, we track business metrics too. Orders per minute, cart abandonment rate, checkout conversion. The CTO doesn't think in terms of CPU usage, they think in terms of revenue. When we can show them orders per minute dropped 40% at 2 p.m. and here's which service is causing slowdown, that's when the monitoring stops just being an engineering tool and it becomes a business tool. It connects what's happening inside of the system to what's happening to the bottom line of the business. And alarms don't just send notifications, they can be wired to trigger automatic responses. CPU spikes across the autoscaling group, a scaling policy launches more servers before anyone even reads the alert. Error rates that may jump above a threshold, the on-call team gets a notification with a link to a runbook. That's a document that a team has written in advance that says for this specific alarm, here's what to check and here's what to do. No guessing and no scrambling. The system tells you what's wrong and the runbook tells you how to handle it. If this had been in place for Black Friday, the autoscaling group would have detected the traffic increase, launched more services, and a team would have been watching it happen on a dashboard in real time. So let me trace what happens when a customer adds an item to their cart. And CloudTrail records AWS API activity across the accounts. Things like someone changing a security group rule, modifying an autoscaling policy, creating a new database, or updating IAM permissions. It logs who did it, when they did it, and from where. It's not tracking every individual read and write inside of your application. It's tracking the behaviors of the infrastructure level actions. If something goes wrong on the next Black Friday and you need to know whether someone changed a configuration that contributed to the problem, CloudTrail gives you that history. Now let me walk you through the entire journey in full, from opening the application to signing up, step by step. Step 1, the customer is browsing a product page. The page itself is images, styling, and layout loaded through CloudFront via S3 from an edge location near them, very fast. Step 2, they tap Add to Cart. That request goes to the application load balancer, which sits in a public subnet across 2 availability zones. The ALB checks which application servers are healthy, then forwards the request to the available EC2 instance. Step 3, the request arrives at an EC2 instance inside of a private subnet. The server picks up the add to cart request. First thing it needs to know, is this item actually in stock? Step 4, the EC2 instance checks DynamoDB for the current stock level. DynamoDB responds with yes, it's in stock, 47 remaining. The EC2 instance IAM role gives it permission to read from DynamoDB's tables. Without that permission, the request will be denied. Step 5, the EC2 instance updates the customer's cart in RDS's multi-AZ. So it adds the item, links it to their sessions, recalculates a total. RDS confirms, the server sends back item added to cart, which flows through back the ALB to the customer screen. Every step is controlled. The security group on these two instances only accepts traffic from the ALB. The security group on the database only accepts connections from the EC2 instances. The EC2 instances use IAM for AWS service permissions, like reading from DynamoDB. CloudTrail records the infrastructure level activity. CloudWatch tracks timing and performance across the whole flow. Now, imagine it's Black Friday. Traffic triples. The auto scaling group detects the increasing load and launches additional EC2 instances across both availability zones. The ALB spreads requests across all healthy instances. Each server handles a manageable amount of traffic. Each one makes a normal number of database connections. No server overwhelmed, no database flooded, and if one availability zone has an issue, the load balancer can continue routing traffic to the healthy instances in the other availability zone. Same 5 steps, same fast experience for the customer. Whether there are 1,000 people shopping or 100,000 people shopping, the architecture handles it in the exact same way. This is why my students are getting hired left, right, and center right now. Literally right now, the job market is hotter than ever. I don't care what your coworker told you, or what fear-mongering the headlines are telling you. I don't care if you think the job market is cooked, or there's no job, and AI is taking everything. I am seeing this from having boots on the ground. AI spending is creating unprecedented demand for talent, but you've probably not experienced hiring managers and recruiters calling you back because, quite frankly, you don't even have the skills that they're looking for yet. And that's fine if you're just coasting, you are vibing, right? You're not even looking for a real cloud role. But if you're a tech right now and you're looking to break in and you're self-studying on the side, knowing that you want to make a switch, or you're already in tech and you're looking to get into cloud, you have to make sure you're building the skills the market is actually paying for right now. There's a big nuance there, and I see it with my students before they even get my help. They are deep in this self-studying route, doing a bit of Udemy here, a bit of YouTube tutorials there, and they are busy. They feel productive, but are not actually getting job ready. And what happens over time is the keeping busy part. All of that activity has actually become the very reason that they are stuck. It's replaced the original objective. Because think about it. When you first started, the goal was to get hired. But somewhere along the way, it became about finishing the next certification or completing the next course. And look, that's not getting you job ready. Today, tomorrow, next year is going to come to you. And you're going to look back and ask yourself, why was I doing the wrong things for so long instead of just focusing on building the skills that the market actually pays for? So if you want my help, check the link in the description below to book a call with my team. More than 900 people just like you have been watching my YouTube videos and made a decision and are now inside of my academy building the cloud skills that the market actually demands. Let's move on to scenario 3, the AI-powered enterprise. Here is the brief. A Fortune 500 financial services company is currently processing thousands of documents every single day. Contracts, compliance reports, regulatory filings, all manually. A team of 40 people opens each document, reads through it, figures out what type it is, pulls out the key information, and routes it to the right department. The process is inefficient, mistakes happen often, and it's one of the most expensive operations in the company. They want it automated. This is a completely different kind of problem from the first 2 scenarios. There is no website, there are no public users, there is no traffic spike to survive. This is about taking a manual business process that costs a fortune in time and salaries and building a system that does it automatically. Now, before we jump to a solution, let's think about what actually makes this problem hard. Firstly, the documents aren't simple. These aren't standardized forms where every field is in the same place. They are contracts with different formats and text. You need something that can actually read and understand what a document says, regardless of how it's formatted. That's an AI problem, so when I see that, I'm already thinking that we need an LLM for this. Secondly, the volume is massive, thousands of documents per day, and they're all different sizes. 1 page or 50 pages. Whatever we build needs to handle that variation without taking too long or wasting resources. Thirdly, And this is the constraint that shapes every single decision that we make. They are in financial services. Strict regulations about where their data can go and how it can be handled because we've got sensitive information here. So when you see this, you automatically should recognize that any solution that you build, you have to ensure that the storage of that data and transferring that data, we cannot have it leave our private AWS environment that we actually eventually build. So the core problem here is that it's slow, expensive, error-prone manual process that needs to be automated with AI at scale, with strict data requirements. The reason why this scenario matters is because right now we are seeing this type of problem explode in the market. Every single one. Businesses across the world are scrambling to implement AI, and if you understand how AI fits into cloud architecture, you are ahead of 99% of people applying for cloud roles today. So let's start with layer one, which is traffic. In the first two scenarios, traffic meant users on the internet hitting a website. This scenario has none of that. The traffic here is the documents, contracts arriving by email, compliance reports submitted through an internal portal, customer correspondence being uploaded by staff. All of these end up in one place, S3, the same storage service that we use in the first two scenarios, but for a completely different purpose. Instead of serving files to users, it's now receiving documents from the company's internal systems. Now, we need to connect the arrival of a document to the system that processes it. And this is where we produce a new concept, a queue. Let me explain why we need one. Imagine that we set things up so that every time a document lands in S3, immediately triggers process it. That sounds efficient, right? But think about what happens at 9 a.m. on a Monday when 200 compliance reports get batch uploaded at once, or end of quarter when thousands of contracts need processing. Without a queue, all 200 documents would try to start processing simultaneously. That meant we need enough processing capacity to handle all 200 at once, which is expensive and wasteful for the 23 hours of the day when documents arrive on a random basis. A queue solves this. The AWS service is called SQS, Simple Queue Service. So when a document lands in S3, instead of immediately triggering processing, S3 sends a message to the SQS queue saying that a new document has arrived, here's where to find it. The message sits in the queue until the processing system is ready for it. The processing system picks up messages from the queue at whatever pace that it can handle. So finishes one document, picks up the next, finishes that, picks up the next. This is called decoupling. The part of the system that receives documents and the part that processes them are completely independent. The upload side doesn't need to know or care how fast the processing side works. It just drops a message on the queue and it moves on. Layer 2, compute. We've got documents arriving in S3 and messages queuing up in SQS, but a queue on its own doesn't do anything. It's just holding messages. Someone needs to actually pick up those messages, grab the document from S3, process it, and save the results. That's the compute layer. Let's think about what we need from the processing side. It needs to be able to continuously read from the queue, pick up a document, analyze it, figure out what type it is, extract the important information, determine where it should be routed, then save the results and move on to the next one. In scenario 1, we use Lambda, and it could technically work here for most documents, but there are a few reasons it's not best fit for this particular workload. Firstly, the documents are large and complex. Contracts and compliance reports that can run dozens of pages, Lambda has a hard limit of 15 minutes per execution. If a single document takes longer than that to analyze, especially when we're sending it to an AI model and waiting for a detailed structured response, Lambda will cut it off mid-process. That's a complete deal breaker for this workload. Secondly, even for the documents that finish within 15 minutes, Lambda spins up and shuts down every single document. That means every execution needs to set up a fresh connection to an AI service, download the file from S3, and initialize any libraries. When you're processing thousands of documents per day, that repeated setup overhead adds latency and complexity. Lambda's memory and CPU options are very flexible, but they're not optimized for sustained processing where you're holding connections open and waiting for detailed AI responses. A better fit here is Fargate. Instead of running a function that starts and stops for every document, we package the processing code into a container, i.e. our code plus the libraries and dependencies that it needs, plus any configuration, all bundled into one unit that behaves the same everywhere that it runs. We hand that container to ECS, Elastic Container Service, and tell it to run it on Fargate. Fargate manages the infrastructure underneath. We don't set up servers, we don't install operating systems, we don't patch anything. We just say, here's my container, run it, and Fargate figures out the rest. The key difference from Lambda is that the container runs continuously as a service. It doesn't start and shut down for every document. It sits there, polling the SQS queue, reading messages one after another. A message comes in, new document in S3, the container downloads it, processes it, saves the results, and immediately checks the queue for the next one. Because it's running continuously, it keeps its connections open and reuses them across documents. No setup overhead each time. And because it's not bound by Lambda's 15-minute limit, a 50-page contract that needs deep analysis isn't a problem. If documents arrive faster than one container can handle, the queue builds up, ECS automatically launches more containers, 3, 5, 6 containers all reading from the same queue, processing in parallel. When the queue drains, the extras just shut down and you only pay for the capacity that you actually need. Now, what does the container actually do with each document? This is where the AI comes in. The container sends a document to Amazon Bedrock, AWS's service for using AI models like Claude and OpenAI models directly from your own code. But because this is a regulated financial services company, we don't send the traffic over the public internet. We call Bedrock through private VPC endpoints using AWS Private Link. The model runs through Amazon Bedrock, and model providers do not get access to our prompts, our completions, or any sort of Bedrock logs. That gives the AI capabilities that we need while keeping the network path private and that data handling controlled. But we don't just send the documents to the AI on its own. If we do, the AI will give us a general answer. It can identify the type of document, maybe pull out some obvious information like names and dates, but that's not what the company needs. They need very specific data points extracted depending on the document type. They need it categorized according to their internal compliance frameworks. They need it routed to the correct team based on their internal procedures. They need deadlines calculated based on their own policies. The AI's general knowledge can't do that. It doesn't know this company's frameworks, policies, or procedures. So we need a way to give the AI that specific company knowledge. That's what RAG does. Retrieval Augmented Generation. And here is how it works. Before the AI processes a document, our system first searches the company's own database and pulls in everything that's relevant from our internal frameworks. All of that context gets sent to the AI model alongside the document itself. So the AI isn't just looking at a contract with general knowledge, it's looking at that contract plus the company's specific framework, plus their routing rules, plus their review deadlines. Now it has the full picture, and a difference in output is significant. With RAG, you'll receive specifically just like you would if a human were to process a document. And that's because we provided the AI model the context which acts as a lens to make the output actually useful. That's the difference between AI that works in a demo and AI that replaces a manual workflow. Layer 3, data. The AI processes each document and produces structured output that we want, but that information needs to be stored somewhere that the business teams actually can use. We can use Aurora here. It's a database that stores data in tables, rows, and columns, and lets you ask questions across that data. Why would we use Aurora instead of standard RDS? Now, AWS took the same concept and rebuilt it to be faster and handle more people using it at once. Same idea, but a way better engine underneath. Why one database here instead of two? Because everyone's asking questions about the same thing. Processed documents. The legal team wants to find a specific contract by client name. The compliance team wants to look across thousands of documents to spot patterns or pull together a regulatory report. Different questions, same pool of data. Aurora is quick enough for the simple searches and powerful enough for heavy reporting. So one database does the job. One thing to manage, one thing to secure, and one thing to back up. You don't always need multiple databases. It just completely depends whether the work is different enough to justify it. Here, it is not. Now, the original document files themselves stay in S3 with versioning turned on. And versioning literally means S3 keeps every version of every file. If a document gets reprocessed 6 months later, the original is still there exactly as it was. For a company that might need to prove what they had on file at a specific date, that's very important. And then what we do is we move older files to cheaper storage. You can set up rules. After 90 days, shift the documents to a cheaper tier on S3 because nobody's looking at them every single day anymore. After a year, it moves into deep archive that costs almost nothing. Set up once and then it runs in the background for you. Layer 4, security. This is a financial services company handling sensitive data. Security isn't something that we bolt on at the end. It's been shaping every single decision from the start. The FileGate containers that process documents have tightly controlled permissions. They can do exactly 3 things: read documents from S3, read messages from the SQS queue, and call AWS Bedrock. That is it. They can't write to the database directly. They can't touch other resources. They can't access anything beyond those actions. If something goes wrong with a container, the damage is limited to what it's allowed to do in the first place. And there's a reason the database write is handled separately. The container is doing the risky work, taking in external documents and running them through an AI model. If there is ever a problem in that pipeline, you don't want the same thing that handles untrusted documents to also have the keys to your production database. Keep those responsibilities apart, and even a compromised container can't mess with your data. Bedrock is locked down the same way. It only has access to a specific knowledge base set up for this workflow, the compliance frameworks, the routing rules, and not the company's entire data sets. Just what it needs for this specific job. CloudTrail logs every AWS API call, who invoked the model, when and where from. For business level audit trails, which document, what was extracted, who approved it, we add application login to CloudWatch and audit table in Aurora. And everything is encrypted throughout. So documents in S3, messages in the queue, data in Aurora, traffic moving between services. At no point is sensitive data sitting there unprotected. Level 5, cost and budget. Let me walk you through the actual cost comparison because this is how you present it to the CTO. On one side, you have the current state, 40 full-time employees, salaries, benefits, office space, training, management overhead, plus the cost of errors, right? A misfiled compliance document doesn't just waste time, it can result into regulatory fines, plus the cost of speed. Documents taking days to process means slow response time to clients and regulators. On the other side, this architecture. Bedrock charges based on how much text it processes. The longer the document, the more it costs to analyze. Fargate changes for the compute time your containers use, SQS charges for messages, pennies per million messages, Aurora charges for the database instance and storage, all being usage-based. At 1,000 documents per day, you can model the exact monthly cost before building anything. You know the average document length, you know the Bedrock pricing per unit of text, you know how many Fargate containers that you'll need based on processing time estimates. The monthly infrastructure cost will be a fraction of what the manual process costs. The business case doesn't require assumptions. It's calculable. We'll set up a billing alarm, which is just a simple rule. If spending goes above a certain amount in a day, send an alert. For a Fortune 500 company, we're not setting this at $50. The normal days spent on this architecture is predictable, so we set the threshold well above that. If it triggers, something is genuinely wrong, maybe a container is stuck, retrying a broken document over and over, and every retry is also a Bedrock charge. Without an alarm, that runs until someone notices the bill. With an alarm, someone gets a notification within an hour. And the architecture is flexible over time. So if a new model comes out that processes better results at lower cost per document, you can just swap the Bedrock configuration and everything else stays the same. The containers, the queue, the database, the security, none of it changes. You just point Bedrock at a completely different model. And instantly you can get better performance. Layer 6, observability and monitoring. The business team doesn't care about how hard the containers are working or how fast Bedrock is responding. They care about one thing. Is this system actually doing the work that 40 people used to do, and is it doing well? So we give them a dashboard with one key number, documents processed per hour. They look at one screen, they see how many documents are going through, how many succeeded, and whether anything needs attention. That's what proves that a system is working. Behind that, CloudWatch is tracking everything technical. How the containers are performing, how fast the AI is responding, how many errors are happening. The team doesn't need to watch any of that day to day, but it's there when something needs to investigating. And if something actually breaks, say a new document format comes in that AI doesn't know how to handle, an alarm fires and the team gets notified. So let's go through the architecture and let me trace what happens when a new contract arrives. Step 1, someone in the company uploads a contract through the internal portal. The file lands in S3. Step 2, S3 sends a message to the SQS queue. New document arrived, here is where to find it. The document just sits in the storage. The message just sits in the queue. Nothing is rushed. Step 3, a Fargate container picks up the message from the queue. It downloads the document from S3. The container's permissions only allow it to read from S3, read from the queue, and call Bedrock. Nothing else. Step 4, the container calls Bedrock through a private VPC endpoint, not over the public internet. It sends the document along with the relevant context pulled from the company's own database through RAG, their compliance frameworks, their routing rules, and review deadlines. Bedrock processes the document with all of that context and returns structured output. Document type, extracted data points, which team it should go to, and what the deadlines are. Step 5, the process results get written to Aurora for a separate control process with its own permissions. The legal team can now search for this contract by client name. The compliance team can include it in their next regulatory reports. The data is there, is structured, and is ready to use. The original document stays in S3 with versioning. Every version is preserved. CloudTrail has recorded every single action, which document, which AI model, when, and what triggered it. CloudWatch tracked how long each step took and whether it succeeded or not. If the queue had been building up, say it's end of quarter and thousands of documents are coming in, ECS would have already launched additional containers to work through the backlog. One document or 10,000 documents, same flow, same security, same audit trail. Now then, across all 3 scenarios, we've designed a complete architecture. But there is something just as important that we haven't covered yet. How does any of this actually get built in AWS? When you're starting out, you can use the AWS console. I call it ClickOps. And that's completely fine when you are new because it's how you learn. That's how you get a feel for what each service does and how things fit together. But if someone's telling you that it's enough to do ClickOps to land a six-figure cloud role, then they haven't worked in a real production environment. Here is why. Let's say that you've built this e-commerce architecture from scenario 2 by clicking through the console. It works. Great. Now, a month later, your team needs an identical copy for testing, and you're sitting there trying to remember which menus you click through, which settings that you chose, which permissions that you configured, and what order you did things in. You can't remember that. So you do your best, get most of it right, but something seems slightly off. A security group rule is different, a database setting got missed, and now you've got a testing environment that's almost the same as production, but not quite. And then it breaks or it just doesn't work as intended. Infrastructure as code solves this problem. So instead of clicking through the menus, you write a file. That file describes everything, every service, every configuration and permission, all in one single place. So you give that file to a tool like Terraform or CloudFormation, and it reads it and builds everything exactly as you described. If you need a new copy for testing, you just run the same file, you change some configuration, and it works. If you need to go for production, again, same file, slightly different configuration. Every environment comes out identical because they've all built from the same source. And because it's a file, you can track every single change. It's version controlled, right? Who changed it, what changed, when, and why. Everything that we've built today, all three scenarios in the real world, none of it gets clicked together through the console. It gets written as code, reviewed by the team, and deployed the same every single time. So you just worked through three completely different business problems. A startup that needed to scale on a tight budget, an e-commerce company that crashed on its biggest day of the year, and a Fortune 500 finance company replacing an entire manual operation with AI. Three different industries, three different constraints, three different architectures. And not once did we start with a service. Every single time we start with the problem. What's actually going wrong? What does this business need? And then the services showed up because the problem demanded them. That is the skill. It's not about knowing what Lambda is or what it does. Knowing when Lambda is the right call and when it isn't. That's the difference between someone who's passed an AWS exam and someone who can actually work in a real production system. And if you can sit in an interview and walk through a problem the way that we just did, layer by layer, explaining every decision and every trade-off, the hiring manager will have no option but to give you the job. If you want my help to land six-figure cloud engineering roles, there's a link in the description below to book a call with my team. As always, I'm rooting for you. Go and become undeniable.